Hi, are you planning to master Amazon EKS service or just getting started to learn containers and Kubernetes? If the answer is yes, you're in the right place. This is a multi-part Amazon EKS deep dive series where we will cover various aspects of running workloads on Amazon EKS. Let's get started. The third breakthrough in our data store architecture is partitioned key space design that delivers up to 5 times write throughput improvement. Kubernetes natively supports partitioning etcd clusters by resource type and doesn't require serializable transactions across different resource types. We leverage this characteristic to implement an optimal partitioning scheme. Ultra-scale clusters benefit significantly by splitting hot resource types into separate etcd clusters. For example, pods, nodes, services, config maps, and secrets can each have their own dedicated etcd partition. This eliminates contention between different resource types and allows each partition to be optimized for its specific access patterns. Our partitioning architecture supports dynamic repartitioning, but we've found that well-assigned static partitions are sufficient to support 100,000 node scale. The system continues to use etcd's rich API semantics that have evolved specifically for Kubernetes over the years, ensuring full compatibility while delivering the performance improvements needed for ultra scale. Moving up the stack from the data store, let's examine the API server optimizations that enable extreme throughput at ultra scale. Kubernetes API servers in Amazon EKS can already scale vertically and horizontally, but ultra scale required specific enhancements to handle the massive traffic patterns generated by 100,000 node clusters. The first major optimization is consistent reads from cache, introduced in Kubernetes 1.31. This feature allows offloading a significant portion of read traffic from etcd to the API server's local cache. Previously, reads requiring label or field-based filtering would force the API server to list entire collections from etcd first. Now, when the cache is current, these reads are served directly from memory, cutting server-side CPU usage by 30% and speeding up list requests by 3 times. Streaming list responses provide another significant improvement. Large clusters have large collections of objects, and listing them efficiently is critical for controllers that need entire collections for reconciliation. Streaming responses improve memory efficiency and increase list request concurrency by approximately 8 times by incrementally encoding and transmitting items rather than buffering entire collections. For custom resources extensively used by ML frameworks, concise binary object representation (CBOR) reduces payload size and serialization overhead by up to 25% compared to JSON encoding. Controllers operating at cluster scope need to maintain a global view of resources to perform centralized operations like pod scheduling. At ultra scale, these controllers face significant challenges: larger state to hold in memory, increased transactions per second on dependencies, and the need to make high volume decisions quickly. The first major improvement addresses lock contention on informer caches. Kubernetes controllers use the informer pattern to efficiently track resource changes by maintaining local in-memory caches. We observed high read-write lock contention when controller worker threads performed large list operations, delaying incoming event processing and causing cascading effects like queue pileups and memory pressure. We solved this by adding optimized indexes for heavy list requests and implementing batch processing for high churn scenarios. These improvements increased event handling throughput by up to 10 times during high churn scenarios. For the Kubernetes scheduler specifically, we achieved consistently high throughput of 500 pods per second even at 100,000 node scale through careful tuning of scheduler plugins and optimized node filtering and scoring parameters. Carpenter is AWS's flexible high-performance node lifecycle management project for Kubernetes. While customers often run mixed general purpose and accelerated workloads in the same cluster, certain limitations prevented Carpenter from being ideal for ultra-scale AI/ML workloads. We evolved Carpenter specifically to address these challenges. The first major enhancement is guaranteed capacity for ultra-scale ML training jobs. These jobs often arrive in batches with specific patterns that Carpenter's reactive provisioning model doesn't anticipate, potentially leading to delays. We introduced support for static capacity through static node pools that maintain a minimum set of nodes consistently, guaranteeing capacity for long-lived AI ML workloads. We also added support for capacity blocks for ML in the node class API. Capacity blocks are ideal for model training, fine-tuning, and preparing for inference demand surges. Carpenter now prioritizes capacity blocks when provisioning static capacity before falling back to other capacity types. For accelerated compute reliability, we enhanced auto repair capabilities. Using Carpenter's node repair feature with EKS node monitoring agent, customers can automatically replace unhealthy accelerated compute instances. We also parallelized various controllers and optimized memory allocations to improve performance at ultra scale. Amazon EKS supports native VPC networking for Kubernetes pods, avoiding overlay network overhead while enabling deep integrations with AWS networking services. Scaling networking to support 100,000 nodes required significant enhancements to address both capacity and performance requirements. The first major change is moving from individual IP assignments to warm IP prefixes. As cluster scale grows, you must plan for network address usage, where each VPC can support up to 256,000 NAUs or 512,000 when paired. Since both an IP address and an IP prefix count as a single NAU, regardless of prefix size, we configured the Amazon VPC CNI with prefix mode for ultra-scale clusters. This optimization, combined with Carpenter handling prefix assignment directly in the instance launch path, streamlined networking with a single VPC for 100,000 nodes while speeding up node launch rates by up to 3 times. For maximum network performance, we enabled multi-network cord support. When training with massive petabyte scale datasets, network bandwidth becomes a key bottleneck. By creating pod ENIs on additional network cards supported by accelerated computing instances, we enhanced pod network bandwidth capacity to over 100 gigabits per second and improved packet rate performance. Ultra-scale AI ML workloads typically use large container images such as PyTorch training frameworks, TensorFlow notebooks, and SageMaker distributions, often exceeding 5 gigabytes. The speed of downloading and unpacking these container images becomes a critical factor in workload readiness at scale. We introduced Seekable OCI Fast Pull, which enables concurrent download and unpacking operations. Seekable OCI Fast Pull downloads large layers in chunks, allowing this step to complete much faster than traditional sequential approaches. We then leveraged the high elastic block store IOPS of 260,000 and throughput of 10 gigabits per second supported by Tran2 and P5E/P6 instance types to reduce unpacking time. Parallel unpacking allows multiple layers to be decompressed and processed simultaneously rather than waiting for each layer to complete sequentially. Our testing demonstrates up to a 2 times reduction in overall image download and unpack time compared to default approaches. Additionally, we created Amazon S3 VPC endpoints in worker node VPCs that guarantee 100 gigabits per second bandwidth per availability zone. This ensures sufficient throughput for downloading container image layers and leads to significant improvements in node readiness times. A key tenet of our testing methodology is working closely with customers and working backwards from their needs to resemble real-world ultra-scale AI/ML workloads. This meant covering a comprehensive spectrum of workloads ranging from large distributed pre-training jobs to multiple concurrent fine-tuning experiments to high-throughput inference serving. Exercising accelerated infrastructure requires clusters to run a variety of device plugins for compute, network, and storage while consuming essential AWS services like Amazon ECR, Amazon FSx, and Amazon S3. Additionally, AI/ML customers commonly install node agents for health monitoring through EKS node monitoring agent, telemetry collection via Amazon CloudWatch agent and NVIDIA DCGM server, application credentials through EKS pod identity agent, and image caching systems. Through extensive testing, we validated that all these core capabilities scaled seamlessly and worked reliably at 100,000 nodes. Our testing scenarios included massive pre-training jobs running on all 100,000 nodes, 10 parallel fine-tuning jobs each using 10,000 nodes, and mixed mode workloads with 70,000 nodes running fine-tuning and 30,000 nodes serving large-scale inference.